Hey guys, and welcome to Functional Print Friday. So we're over here at the milling machine today, and for those of you that are subscribers to the channel, you might remember when we made these covers for the table on the milling machine. There's two pieces on each side. They interlock together and they cover our precision ground table so that we don't damage it in case we drop something, and also just keeps the chips from getting all over it as well. It's a lot easier to vacuum this out, and it's got kind of like a tool tray set up on it as well. So if you haven't seen that and you're interested, you can go down and check it out in my videos. But today what I want to talk about is installing a DRO on this mill. Now, they do sell this mill with a DRO. When I bought it, I had the option to buy it. I chose not to buy it initially because I kind of just wanted to get used to the machine first and get a feel for everything. And I thought, maybe I don't need it, right? I've run a lathe without a DRO. I never had any issues, but on a milling machine, it really is kind of a pain because your backlash is really difficult to work around in 3 dimensions. So what I mean by backlash is I can turn this handle a good bit in each direction before the table moves. A milling machine has 3 different axes, just the same as a 3D printer. You have your Z-axis up and down, you have your X-axis left and right here in the frame, and you have your Y-axis, which moves in and out, and that's all in relationship to the spindle. The Z-axis, you're actually moving the spindle itself rather than moving the table on a bench mill like this. On a knee mill, the spindle stays stationary and the whole table actually goes up and down. And I can move this with these hand wheels on either side. But you see, this distance here, and I know you can't feel that, but I'm moving the handle this distance and it's not actually moving the table. So that makes it a real pain to get up on a specific measurement, because if you overshoot by even a little bit, you got to come back, take the backlash out of it again, and then come back and then try and hit your measurement and lock your table before you mill or drill. So I realized I wanted to do a DRO on this. Now, they also sell the DRO kit for this mill separately. I can buy the whole kit, the scales that read the position of each of the axes, and the DRO head that gives you the numerical readout for this. I opted not to do that as well, mainly because I wanted to check out this TouchDRO system. All right, what is TouchDRO? So I'm going to try not to go on too many tangents in this video, but it's tough because we're talking about a lot of different things. So normally your scales, this is the X, Y, and Z cables from the scales on this mill, would plug into like a big head that has a graphical display on it that shows you your position of your X, Y, and Z axis. This has no display. Instead, it's just a circuit board in there that is reading the value from the scales and then sending that out via Bluetooth. Well, actually does some intelligent processing in here and remembers the position of the scale. But then it sends out that information to Bluetooth, and an Android tablet connects via Bluetooth. It has to be an Android tablet. You can't use iOS. But thankfully, Android tablets are really cheap. This is a brand new Lenovo M10 something or other, and it was like $160. No comparison to what it cost to pick up an iPad. So anyway, I wanted to do this because a normal DRO head has, firmware or software that runs in it, and that's pretty much it. Whatever it does out of the box, that's it. So kind of imagine getting into 3D printing, buying a 3D printer, and only being able to do the things with it that were available at the time you bought it, right? So if, other general features were added to slicers, whatever else, you couldn't take advantage of it on your printer. That would totally suck. And that is why I went this route on the mill for DRO, because not only can the software be upgraded on this guy, but it's just an app running on a tablet. The app gets updated all the time. They're always adding new features, cool stuff. No affiliation with these guys, but really, really happy with the experience. This is purchased from a site called Yuri's Toys, and I had to assemble it. The circuit board itself was pre-built. I didn't have to do any soldering, but I did have to assemble the case, and assemble the pin headers for the DRO connectors, just because there is some variation in how those things ship. Also want to point out, this case is 3D printed. I didn't print this. It came with the kit, and really, really impressive quality. It looks like he's using the Galaxy Black. I don't know if he's using this stuff from Prusa or if it's a third party. It doesn't matter. It looks wonderful. It's not printed at a 0.1 millimeter layer height, but the quality still looks really, really good. I think it's printed at 0.2. Really, really nice, clean prints. So often I see 3D print kits ship out, and the quality of them is just, it's abysmal. Like for anyone that gets them, I can see why they'd never get into 3D printing because, you know, stuff is falling apart, it's cracking apart, the layers aren't all bonded. The quality of the 3D prints that you get in this kit is exceptional. So great job, Yuri Toys. And here's the interface for this. So we have the readout of our X, our Y, and our Z axis. And there's all sorts of other cool stuff we can do on here. And for those that are not familiar with milling and you know what you would want a DRO for, I'll give you a quick demo. So let's say that we want to drill a hole in this piece of stock and we want to drill it exactly in the middle. That wouldn't be terribly hard to do, right? We could blue this up with some, you know, a blue marker or some layout fluid. Measure the width of this with a digital caliper and then scratch a line in the middle. But then how do we center up the spindle of the mill over top of that line? Well, I mean, we could put a point in here and we could eyeball it. We'd probably get pretty close. But what if I told you this thing made it even easier? All right, I got you in a tripod. Hopefully everything is in frame. So what I have here on the spindle is an edge finder. This is this sort of wiggles around here and runs true to the top part of the shaft when it is up against a flat surface. So what we're going to do is we're going to come in and we're going to find the edge of this side, and then we're going to go in and we're going to find the edge of this side, and then the DRO is just going to tell us where the center is. Okay, so we've found both edges. Right away we can already say, all right, well, this piece of stock is exactly 1.2061 inches in width. And we can switch this guy to millimeters with just one click as well. But now where's the center, right? So I can click on this axis, I can tell center, and now it divided that in half. Well, why is that useful? Well, now all we got to do is just, let's go up. So we clear the stock. And now all I have to do is move X until we zero that out. Once we are at 0, by the way, this is what I mean about that backlash. See, I went past it and I don't need to worry about trying to bring the handle back. I can just start turning in the other direction. I don't need to preload it. All right, that's close enough. So this digit here is 5/10 or 1/2 of 1,000. Whatever we're going to bore this hole with isn't going to be that accurate anyway, so that's close enough. But you get the idea. We are right now in the very center of the stock. And this is just a simple piece of material, so I mean, that wasn't terribly valuable, but you can see how this would be really useful in very complex objects that you're milling, particularly if you can't easily measure it with a caliper or something else. What else can we do? Well, check this out. So let's say we wanted to actually bore 5 holes here to mount maybe a flange or something like that, but we wanted them all to be in a circle, so a bolt circle. But it's a small piece of stock, so let's say we wanted to do a really small one. Bring it down closer to the DRO. All right, hopefully you guys can see that with all the glare on it. My apologies. So we have a tool here called a bolt circle, and if I hit this, we can tell it, let's see, circle radius. So it's a pretty small piece of stock, so that our radius is going to be pretty small, maybe I don't know, 0.3. And number of holes. Let's make 7 holes. And we hit create. And now if I expand our side here, we have a list of positions. And that is all of the positions that we need to actually drill the holes in. And I can click on each one of these and it will adjust our readout here that all I need to do is bring them all to 0 and we will be in the position of that first hole. So if I crank this guy this direction, and Z we don't need to worry about, that is our vertical, at least in this type of operation. Now we would need to worry about it if we were trying to drill to a specific depth, but there we go. So we're zeroed out. We could bore our first hole, and that's the first hole in that bolt circle. We can click the second one. And okay, well now we just bring these to 0 again. Unlock our axis. And there we go, we're pretty close. So that would be our second hole. But I know what you're saying, Rich, any DRO can do that. You're right, any DRO since probably like 1980, you know, could do bolt bolt circles, you don't get a nice dialog box to fill in. You're pushing all sorts of buttons and trying to read abbreviations on the screen. But check this out. There is a graphical representation of our workspace. I can zoom in on it. So there's our bolt circle. So first of all, we can visually see, yeah, that's what we really, God, that glare is terrible. Let's see if I can just handhold you guys. All right, that's a little bit better. So I don't know if you can see the difference here. So we can see our 7 holes for this bolt circle, and this one is green. That's because that's the hole that we're on. And we don't even need to now click in this view. We don't even need to click which hole we want to go to. If I want to go to, say, this hole down here, I can just start traveling towards it. You see my crosshair is moving, and as I get close to it, it automatically selects it. So now I can look at the crosshair to get pretty close, and then I can look at the numbers up there at the upper right to fine tune it. And there we go, that's pretty close. So let's say I wanted to skip over to this one for some reason. Notice I didn't need to move the y-axis because these guys are in the same position on the y-axis, just the x changes. And there we go, it's pretty close. All right, enough about the TouchDRO software. It's a 3D printing channel. What are we doing here? Well, as I mentioned, you could buy this milling machine with the DRO kit pre-installed. Ships to you with it all installed, ready to go. They also sell the DRO kit separately. So I could have bought their kit, bolted it up, used their display. Chose not to do that because I wanted to do TouchDRO. I could have still bought their kit, used all the scales and everything that bolts right up, and then just thrown out the DRO head or sold it on eBay, whatever. And instead also picked up TouchDRO and just connected the scales to that and then picking up the tablet. Didn't want to do that either, mainly because of cost. Their DRO systems, I think, start at $800 and go up to like $1,200. I wanted to be way below that for everything. So I chose option C, option D. I think we're at option D, where I was going to buy everything separately and just figure it out as I went. So that means I needed scales for each one of the axes. This is the one for the y-axis here. This measures the position of this. So there's a long part here that on this axis mounts to the casting, and then there's a head down there that moves back and forth and reads the position of the axis. So each one of these has 3D parts on it that make it fit on this machine. I did choose to buy the bracket kit from Precision Matthews. I figured it'd be nice to have at least a starting point. And that is all these pieces here. And for some of the axes, it actually made it pretty easy. So I started with Z. That looked like it was probably going to be the easiest. That's our axis over here. And if we walk around the machine, all right, so here we are looking at the Z axis, and you can see this actually would have been pretty tough without the bracket kit. Because this machine gets wider at the bottom for rigidity, there's a steel bracket up here at the top that spaces our scale away from the machine. And then at the bottom, it does just mount right to the casting. There's some shims in here to keep it from twisting. It did have a little bit of a twist the way that it was first mounted. And then there's another bracket that attaches to the head of this machine. This is the part that goes up and down. And that comes over and holds our head so that the head itself moves up and down when we crank the handle up here. So that this head here is moving up and down in this slot. This axis did turn out to be the easiest. Here's our 3D printed part right here. I was able to flip this piece, the orientation of this mounting bracket. And then once I flipped it, all I needed to do was just create this piece here that essentially shifts us over so that we can get to the back of this reed head. These reed heads aren't actually designed to be mounted from the back, but they do have a set of threaded holes back there. I don't see any reason why you can't mount it from back there. So I did opt to do that. And this basically just offsets that. You can see I marked it as Z. Next one I did is the X-axis, and that is our long axis here. And that one is super tough to see. Let me see if I can find a position where you can see it. Actually, it might just be easier to show you the bracket that they give you for that part. So that is, let's see, where is it? That's this guy here. Hard to get a sense of scale, but this piece of rubber back here to keep chips off of our ways for the y-axis. Just mounted up against the back of the casting for the saddle. And it just mounted with a piece of steel, just a thin steel plate. And to mount the bracket for this, we remove that thin steel plate and instead replace it with this bracket here. And this guy's actually pretty big. Again, it's just kind of tough to sense scale here. And what this does is it gives you a pocket in here where the head of the DRO is able to mount inside of to read that scale as you're moving that axis back and forth. All right, this one is just super hard to see because it's so far down in there, but there is a, this is the, let's see if you can see the end of my finger, that's the reed head itself, and then this piece back here is the metal piece that they supply with the reed head to mount it to the machine. And there's a 3D printed piece that wraps all the way around the lower part of that bracket that actually retains two nuts and also spaces it exactly the distance away from the edge of the front face of this bracket so that it is directly underneath the scale when it's all stacked up. And then it is retained by bolts that go all the way through. So they go through here, this piece here, which is also 3D printed, I'll get to this. They go through the rubber cover here, through the front of the 3D print, through that metal bracket, and then into the rear of the 3D print where the nut is retained. So not only does this sort of hold part of the hardware, but it also spaces it positions the reed head exactly where it needs to be so that it's perfectly aligned with the scale. All right, I moved our head up and I moved the y-axis out so we have just more room to see in here so I can show you the second 3D print for the x-axis, and that is this chip guard here. Normally this piece here, this rubber piece, just attaches to the back of the saddle and you wouldn't have a scale or anything else here, so all the chips just fall into this and you're good to go. Once you install their bracket for the DRO, you've basically just got this steel trough back here that's open at the top because this attaches to the other end of that trough. So you've got an opening, at least the width of my thumb, for chips to fall down in there, which, you know, they're going to be a pain to clean out. But the bigger problem is that's where your reed head is. And the chips and, you know, any cutting oil, anything like that is going to interfere with that over time. And it's going to be a real pain to clean out because there's just not a lot of room to work in there. So I designed this piece that replaces the thin piece of sheet metal that bolts this guy to that bracket that they give you. And also acts as a cover that comes all the way up here, and there's like a paper thin gap between the top of this guy and the bottom of the aluminum cover for the scale, so that as chips bounce around in here, whether they come down over the back or hit this and bounce back in this direction, they can't get into that area. They just fall back down into here. In fact, if I come over to the other side, you can see the part of the trough here is still exposed. This has a solid bottom, so I can't stick my finger all the way through. And this side, I think I'm gonna add another 3D printed piece over here that just basically fills the trough on this side so that chips can't accumulate in there or get in there and then work their way in that direction. So that's one print still to do on this. So while we're over here, this is the reed head for the y-axis. And it is at the bottom of this steel bracket. And this bracket was supplied with the kit that I bought from Precision Matthews, but it's mounted in reverse. The way that they have you use it, this is rotated 180 degrees from how I have it. So these curved surfaces are facing in this direction, which obviously means it's gonna sit further out in this direction. And then the reed head mounts to the bottom of it in their configuration. What I did, again, since nothing's going to line up with the parts that I purchased, I flipped it around and I spaced it a little bit away from this with a 3D printed filler piece that also includes our mounts for that reed head at the bottom. You can see the back of the bolt there. And in fact, come back around the front. I actually have a piece I can show you here. So one concern I had with this setup here is if chips bounce down here, they could potentially get in this little gap here and then drop down where our reed head mounts. So I tried making a revised part that has sort of a like a chip guard there. I got lazy and tried to do it as one piece because this print's standing up like this. So that's a 45 degrees, so I didn't have to have any supports there. I didn't want to mess up this face down here since that is where our reed head mounts to. Not happy with this because it still leaves too big of a gap there because that 45-degree slope. So I think I'm going to do it as two pieces where the guard just presses into some holes with some dowel pins. But this is, otherwise, this is what that piece looks like. So it's just basically filling the entirety of this steel piece here. You can see at the top we have the integrated spacing away from this shaft here, and at the bottom we have the mount for that reed head. It just bolts through here. Also, the original holes in the bottom of this steel piece, you can see the two screws in there. It's also retained, that 3D printed piece is also retained through the steel, through those holes as well. Again, just to add rigidity to the whole thing. So the last print on here is actually around the back. One of the challenges with installing a DRO on any machine is they give you all of this cable, and it's this stainless steel, not braided, I forget what they call this stuff. It's like a flexible material. But what do you do with all of it, right? So what I did was I made two 3D printed plastic spools that have a recessed screw that just mounts into two holes in the casting. And that was basically give me a base to start wrapping all of the extra cord around, because the length is not going to be the same for each of these, right? They all need to terminate up here at the TouchDRO box, but they're all starting in different places. So each one of them have different amount of wraps around this, and then it's tucked all behind there, but the final run that goes up just drops down and just makes a U shape, and it's bundled up in the zip ties here. So of course I'll be posting all the STLs for this for free. If you happen to have a PM728 VT milling machine and you want to go TouchDRO, these are probably going to be of great value to you. If you're in the market for a benchtop milling machine, I am very happy with this machine so far. I don't have a ton of hours on it, but it's a Taiwanese import rather than a Chinese import. The Chinese stuff is really hit or miss. The Taiwanese stuff is generally pretty good, and I'm very happy with this machine so far. Guys, as always, thanks for hanging out in the shop with me. And if this is your first time here on the channel, I do a new video like this every single week, every Friday. It's always something functional. Might be out here in the shop, could be in the house, might be outside, fixing something, improving the functionality of something, sometimes just totally from scratch designs. Also feature other people's designs as well. So you can contact me on my webpage, fpfdesigns.com, if you want to submit your design for me to feature on the channel. Guys, if you enjoyed this video, do me a favor, hit that like button. Not only does it help out the channel, it also tells YouTube what you like, right? Maybe you'll see less videos about like horses and mushrooms. Unless you're into horses and mushrooms, then that's fine. But just saying, if you hit the like button on the videos you like, you're going to see more stuff that you like rather than, whatever YouTube thinks you should watch. And guys, if you really enjoyed this, hit the subscribe button. And if you do, I'll see you next Friday.